Hi team, we're looking at the Specialist Maths Unit 1 Practice Exam questions for 2016. We're going to look at complex numbers and some vector work. Alright, so let's get to it. Let's just clean the board and we'll start fresh. Okay, so first off, question 1. We've got the polar form of a complex number, -3 minus root 3i is. Okay, polar form, it's your r cis theta. So we have to work out what is the modulus of the complex number r. So use your square root of x squared plus y squared. There it is. We plug the numbers in, and you're always going to get positive, because you always, when you square a negative, it's always going to give you positive. So we have an addition there. Root 12, which is 2 root 3. And then the angle, we're going to use our inverse tan of y on x. Imaginary divide reals. Okay, so we've got negative root 3 on neg 3. Now, Mr. Calculator is going to give you this as a possible answer. So if you put that in your scientific calculator or your CAS, hit enter, it's going to give you a pi on 6. But, little check of the unit circle, and we see a negative 3 in the reals and a negative root 3 in the imaginaries is down here into quadrant 3. So we're going to have to add pi to it, and we'll get a 7 pi on 6. Okay, so you correct it there. Now, however, if we look for our 7 pi on 6 in our answers, it's nothing's there. No. So for the negative, coming around this way, it's in the same position as a negative 5 pi on 6. Okay, so it gives you your Z there, 2 root 3 cis negative 5 pi on 6, and that's option B. So you've got to look for both the same angle position if it was in the positive, going around from 0 in positive direction, or going backwards in the negative direction to that same position. Alright, now question number 2. So if the argument of z is given by 19 pi on 6, then on an Argand diagram the complex number z would lie in the which quadrant? So draw up a little unit circle and we can see 19 pi on 6. Well, that's an 18 pi on 6 plus 1 more pi on 6. And that's going to break down nicely into 3 pi. So 3 pi is starting at 0, going around once, going another 180 degrees twice, and then third time over here. So 3 pi on 6 is on the negative x-axis. Now let's add 1 more pi on 6. Comes down into the third quadrant. There it is. Let's do the next question. So question 3, the Cartesian coordinates of the point with the polar coordinates 2 cis pi on 4. So what's that in Cartesian form? Okay, so what we're doing is seeing that the real number of the Cartesian form is 2 times cos of pi on 4. That's 2 lots of 2 root 2, which gives you a value of root 2. And then we do the same for y. The imaginary part, y, well, that's 2 times sine pi on 4. And we get 2 lots of root 2 on 2. And we put them together. And we have it. Okay, so that gives you option A as your answer. Okay, so remember the 2 rules there, r cos theta for the x and y is r sine theta. Okay, so the next question for this complex number, the argument of z is equal to. So finding the argument of a complex number, we can work it out at using your inverse tan rule of y on x, of the imaginaries divide the reals. So there's our rule there. We have an imaginary number, part of the number of root 3, divide the real part, -1. Now the calculator is going to give you this as your result, negative pi on 3. But we have to do a little quick check of the unit circle, and we see for a negative reals and a positive imaginary, there it is over in the second quadrant. Okay, so we have to correct this angle by adding pi to it, to get it from the fourth quadrant over back to the second quadrant. And there's the 2 pi on 3, which is option A. Alright, next question. So for negative 2 root 2 plus root 3i, we have to work out z multiplied by z hat. So z hat is the conjugate of the complex number. So there's z, our complex number, and we're going to multiply by the conjugate. And all you do is change the sign of the number in front of the imaginary part. So where it was a positive root 3i, it becomes now a negative root 3i for the conjugate. And now this is a difference of two squares algebraic structure. So it's the first number squared, that's going to give you an 8, plus the second number squared, that's going to give you a 3. But we have to subtract there. But the plus comes from the I squared. Well, the I squared is a value of negative 1, so it adds up after all. 8 plus 3 is 11. Spot on. Alright, how are we doing so far? Let's try number 6. So the solutions to the polynomial equation 2 times z squared plus 1 is equal to 0 over the complex plane, number plane. So we're solving this little quadratic. So let's use inverse operations. Subtract 1, then divide by 2. So then we take the square root of the right hand side, and can't forget the plus and minus. So here we've got the square root of a negative number. Well, we're going to use the I to represent the square root of negative 1. And there it is, we've got 1 divide root 2i and negative 1 on root 2i as your solution. There it is, option D. Question 7. So we've got a complex number, 2 cis pi on 6, and we have to work out the argument of that complex number to the power of 4. Well, that's use of Demoivre's theorem, which says that any complex number in the polar form, raise it to the power, or it could be anything, a power of n, then you take the modulus raised to the power of n, and then it's cis of n multiplied by the angle. So if it's to the power of n, then you n times the angle. So let's do that. So let's work out w to the power of 4. So we've got 2 to the 4. We don't really matter about that because we're after that argument. And then we've got cis of 4 multiplied by pi on 6, which is a 2 pi on 3. So then the argument of the complex number is just 2 pi on 3. There it is, option B. Alright, so now here we go, question 8. And the Argand diagram has two complex numbers, z1 and z2, and it's shown there. Okay, so we have to calculate this result, I times z2 plus z1. Okay, so the diagram there, the graph, little distractor, but you could apply the geometric transformations. When you multiply by I, what happens is that it rotates by 90 degrees, and then when you're adding z, you can treat it a little bit like vectors. Okay, let's see what happens. So set it up like this, I times the first complex number, negative 3i plus 2i squared. Well, there's something to notice. And that becomes a negative 1, so I've put a negative 2 there. And I've collected my real parts, 5 on 2, subtract 2. And then the imaginaries, negative 3i plus 3i. And we get a half. 5 on 2 take 2 is just a positive a half. Voila. Okay. So now let's look at some vector questions. So which one of the following is a unit vector that is opposite in direction to this vector? Alright, so the unit vector, there we go. U hat is equal to u, divide the modulus of u. So you set up vector u, then you divide by the modulus, so square root of each component squared. And we simplify it. Now, we have to make sure, because we're after the opposite direction, got to chuck a negative sign in front, and that will switch it 180 degrees in the opposite direction. Alright, so distribute the negative to each term, and we can simplify the denominator, and we'll get square root 56. Now, we've got a common denominator of 2 in each term. The 2, 4, 6, well, there's a common denominator of 2. And the surd becomes 2 root 14. So let's cancel out that common factor of 2, and we get this, which is option A. Alright, 10. So we have the vector u is defined by the directed line segment from negative 2, 3 to 3 minus 2. Now if u equals xi plus yj, then the modulus of u is equal to. Alright, so first off, we've got to work out what the vector is from those points. So we take the difference between the x coordinates for the I part plus the difference between the y coordinates for the j part. Gives you a 5i minus 5j. Now let's take the modulus of that. Root 25 plus root 25. Well, there it is, 5 root 2. Option A. Now, 11, we have a vector defined, A and B, but A has this unknown part in it, which we have to work out. And we're told that these vectors are parallel for a particular value of m. Let's work that out. So parallel vectors is given by that definition. That's the same vector in the same direction, just of a different size. Okay, so you equate the two vectors. There's vector m, vector A with unknown parameter m equals k times vector B. There it is. So let's look at the k component in there. So you get an 8 equals negative 6k. So negative 6 times the k and equal to 8. And from that we get a negative 4 on 3 as your value. So let's test to see if that value is correct using the j component. And we'll see that it works nicely. So then we do the last thing for the I component and calculate what m is. M is equal to negative 3k, and we get m is equal to 4. Alright, well, we've done well. Keep going. Question 12. So we've got O to A vector and O to B vector, then A to B and the modulus of that. So let's do that. A to B is given by this, so you achieve that through vector addition. O to B, take O to A. Now we take the subtraction, the difference of the x, y, and z components. And carefully doing that, we'll get this vector through for A to B. Now we have to do the modulus of that. There we go. Put it in the rule carefully and evaluate. And we're going to get square root 45, which is 3 root 5. Alright, so the unit vector for u is equal to 6i minus 8j. So the unit vector, here we go. Vector divide the modulus. You carry out the substitution. You notice that there's a common factor of 2, and we're going to cancel that out, and there it is. 3 fifths I minus 4 fifths in the j, and that fits with C. Alright, multiple choice, not bad. Let's look at some short answer problems. So straight away, we've got 3 vectors, vector A, B, and C, and we have to evaluate these expressions. So the first expression, 3 times A plus 4 times B minus 4C. Alright, so it's simple substitution. So you substitute into each the vector with in brackets, and then you expand the brackets and collect the i's, collect the j's, and collect the k's components, and simply we'll get a minus 3i. Same next part, A times B divides C. So again we substitute them in. There we go. Oh, these are just complex numbers. Okay, so what we're doing here, we've got a complex number times a complex number, so distribute by expanding the brackets. There we go, we've got this I squared. Divide by this negative 3i. Now, when we divide by a complex number, we've got to rationalize it by multiplying by the conjugate. So the conjugate of negative 3i becomes positive 3i, and we have that as a fraction on top of itself. We've got this 4i squared, so make sure that goes to -1 times 4. And we will get it simplified nicely, 1 minus 5 on 3i. Okay, next part. So solve the quadratic equation 3z squared minus 12z plus 13 is equal to 0 for z. Okay, where we're told z is a complex number. So, quadratic equations. Let's solve a quadratic using our general quadratic formula. There it is. Okay, so we've got a value of 3, the b value of minus 12, and a c value of 13. So substitute that into general quadratic formula. And simplify carefully. And you'll get down to here. 6 goes into 12 twice. Now we've got square root -12. What's going to happen? Well, 12 is 2 root 3. And we've got the negative, so we take out an I. And we simplify it. The 2 divides into the 6, and we have root 3 on 3. There it is. Okay, show that this expression simplifies to minus 3 root 3. So simply here what we're doing, we're rationalizing the denominator. So divide by -I, well, instead we're going to multiply by the conjugate on top of itself, I divide I. And -I times I will just give you 1. It'll be a -I squared, which is negative times -1, positive 1, and distribute your complex I through to each term, and you will achieve that. Okay, then we have part B. Express minus 3, subtract root 3i in polar form. So this is r cis theta, so we're going to convert it to polar now. So let's work out the r. Oh yes, very important. I squared is equal to -1. Let's work out the r for this question. So we square each part, -3 squared, and plus root 3 squared. There it is. You get 2 root 3. Now let's work out the argument. So the inverse tan rule of negative root 3 divided -3. Well, that will give you positive pi on 6 in your calculator, but you've got to correct it. Plus pi, 7 pi on 6. And put it together for your complex number. There it is. So make sure you always do that unit circle check, and you have to correct the angle if it's not in the right quadrant. Question 4. Now, we've got z is equal to 2 cis pi on 4. We've got to work out z to the power of 3. Alright, so it's like a Demoivre's theorem. Z to the power of 3, we take the r to the power of 3, and then we have cis of 3 times pi on 4. It gives you an 8 cis 3 pi on 4. Now, cis, because we're converting it to an x plus y in Cartesian form, let's expand what cis is using its definition. Cos of the angle plus I times sine of the angle. So, cos of the angle, that is cos of 3 on 4 is negative root 2 on 2. So 8 times negative root 2 on 2 plus 8 times positive root 2 on 2 times I. And then we simplify. And we achieve that. Alright. Now, we've got 3 complex numbers in question 5, z1, z2, z3, and we have to answer the following. Now, as you notice, these complex numbers are all given to you in polar form. So we're going to use operations with polar form. So that's going to involve, if complex numbers are multiplying, you can add the angle. If complex numbers are dividing, you can subtract the angle. Remember those ones? Okay, so let's multiply. So I've got z1 times z2 times z3, and I can write that with them all in brackets. So now the r numbers multiply. There we go, you multiply out the r numbers, and then you add the arguments. We get a common denominator of 6, and that's going to reduce to 0. 6 cis of 0, which is just the number 6. Okay, determine the equation. Now we're going to divide. So you multiply the first top 2, and then divide by the third complex number. So you multiply and divide the radius, the modulus, and then the top two angles are going to add, and then the bottom angle is going to subtract. Add and then subtract. There it is. There's the subtraction because it's a division. Common denominator is 6. And that simplifies nicely to minus pi, which will give you a negative 3 on 2. Alright, so now we express the multiplication result and the division result in Cartesian form, and we've kind of already did that. There it is in polar form. In Cartesian form, it's 6 plus 0i. And then this one again, converting to Cartesian form, you should get 3 on 2 plus 0i. Fantastic. Okay, now D, let's represent these on an diagram. So simply we can draw a line segment from the origin to the point, 6 in the real, 0 in the imaginary, so it lands on the x-axis, and same in the other direction. Negative 3 on 2 in the reals and 0 in the imaginaries. Vectors. Okay, so let's evaluate some vectors. So again, you've given A, B, and C vectors, and we're going to evaluate 2A minus 2B plus 5C. So substitute into brackets, expand out the brackets, and collect your I, J, and K components. And you add and subtract carefully, and you should get something like that. So that's fairly straightforward. Now this one, the modulus of A minus B plus 2 times the modulus of C. Now, we're going to work out what the A minus B is first, and then do the modulus after. So we can write it. There it is. There's vector A, and we're subtracting vector B with the modulus on the outside. So you work that out by doing the subtraction. Then now we're ready. Let's take the modulus of those vectors. And then simplify your square roots. We get square root of 68. Now, you have to check, can that third be simplified? Yes, it can. 2 root 17 plus another 2 root 17 gives you 4 root 17. Haha. Not bad. Alright. Question 7. Now, if vector A is that and vector B is that, then let's first find the unit vector of B. So we're pretty good at that. So it's your B hat equals B divide the modulus. So simplify that square root, and you get 1 on 7. Now that stays as just the factor at the front of the brackets, and you can express the unit vector just like so. Alright, part B, find the scalar resolute of A in the direction of B. Now think about what that is. A in the direction of B is describing two vectors that are parallel. Okay, so here's the formula for finding the scalar resolute. Remember, that's the bracket part of the main formula. So this is a scalar value. You're going to get a 1 unit at the end, 24 over 7. Okay, so make sure you carry out the dot product carefully. The i's multiply plus the j's multiply, then plus the k's multiply. And take this 1 over 7 for fraction, bring it out the front first, and then save it there to the very end. What's important to realize here in this first vector, if you don't have any j component, so that you've got a minus 5i plus 3k. There's no j component, so you have to use a value of 0 for the j. Okay, so there's your 0 times 3. Make sure you do that. Alright, find the vector resolute of A in the direction of B. So there it is, vector resolute, the whole lot. This time it's multiplied by the direction to make it a vector. So we've worked out the bracket. There's the first bit. So you just need to use that now and then multiply by the dot product. Sorry, multiply by the unit vector. Okay, so the last part D, find the perpendicular resolute of A in the direction of B. Here we have, there's the rule, vector A minus the parallel component. So you set up vector A, then you subtract the part we worked out in the previous question, that bit there is the parallel component. Now we've got some nasty fractions, so you've got to work through it carefully. The best way to do it was to set up a common denominator of 49. That's that denominator there. And we think about it as -6 lots of 49, and then we're adding 140. So if you're doing the fraction addition subtraction carefully, you should get something set up like this as your final vector. Alright, make sure you be careful with little operations like subtracting a negative here, and again subtracting the negative 48 and 49k. That's going to become an addition, so you make sure you add. So you have to carefully follow your operations to evaluate that. Alright, so this question 8, solve for the angle between vectors E and F. Give your answers in degrees. Let's do that. You have to use your dot product rule involving the cosine of the angle. So I have cos theta is equal to the dot product of E and F divide the modulus of V times the modulus of F. Alright, so let's do those parts. So you set up in the numerator a dot product, vector E dot with vector F we're going to carry out up top, and then you've got the modulus, here it is, the square root of each component squared. When you do the dot product, it'll be a -4 times -4 gives you a positive 16 plus 4 times 3 gives you 12. There it is. So when you carry out that and simplify it nicely, you're going to get this. You're going to get a 7 over 5 root 2, which is 7 root times root 2 divide 10. Now, to get the angle, we have to do the inverse cos of this number. So inverse cos will give you an 8.13 degrees. Nice. Question 9. We've got a pyramid. A, B, C, D, E pyramid. So in terms of I, J's and K vectors, let's work out these guys. So this is quite straightforward. All we're doing is taking the difference between the coordinates for in the I component, the J component and the K component. Okay, based on the X, Y and Z coordinates. So some things you can notice. Once you've got vector A to B, that's this line here, A to B, there it is. Well, we can see, hey, that's parallel to D to C. But C to D is just the negative of it, going in the opposite direction. Okay. Now vector B to C, going this is this one up top, running this way. Well, there it is. When I do the difference between the coordinates in the I, J and K component, I just get 6J. And A to D, going that way, well, that's parallel. So A to D is equal to B to C, which is the same as just 6J. So that one's not too taxing, quite straightforward. And I think we pretty much are done. So that's the practice exam, folks. Good luck with the real thing.